What's up, everybody? Happy Sunday. It's good to see you all. I wanted to make a really quick video recording just in response to one of the quiz questions from the quiz that you took this past Friday. And this would have been Friday, April 3rd. So there was one quiz question, I think, this was on skill 20, one quiz question that I think was far and away the most challenging for you all, in the sense that I think the large number of students felt like they didn't really have a strong handle on how to proceed. So I wanted to talk about that problem and then talk through that problem, telling you how I might approach that problem and what answer I would ultimately want you to arrive at. Let me go ahead and pull that up right here. Okay, and so here's the question. Consider the function f of x that is given in the graph below, right? So just to be clear, this function right over here, this is going to be our function f of x. Suppose we know that the total integral from 1 to infinity of our function is equal to 8. So that's one piece of information that we can sort of anchor around. Let's let a sub n, a sequence, be equal to f of n, and consider the series sum as n goes from 1 to infinity of a sub n. Which of the following can we definitively conclude? Circle an answer and explain our answer. Okay, great. So let's talk about this. First, let's make sure that we understand the prompt and what's sort of being asked of us. So again, this is our function f of x, right? This function right here. We are claiming that we have a sequence, which I'll go ahead and draw in blue. And the sequence is going to be given by a sub n equals f of n, right? So this would be a sub 1. Let's try that again. This will be a sub 2. This will be a sub 3, a sub 3. This will be a sub 4, and so on and so on. Right, so just to be really explicit, a sub 1 will equal 4. A sub 2 will be something just a little bit north of 2, I suppose. That's like maybe 2.8. Right, I should say just something a little bit south of 3. A sub 3 will equal 2.2, let's say, and so on, etc. I'm not actually going to care that much about the specific values so much as I just want to highlight exactly how we're defining this function. And then we are defining a series. This will be the series as n goes from 1 to infinity of a sub n. So that's these different values, a sub 1 plus a sub 2 plus a sub 3 and so on, right? Okay, and the question is, what can we conclude about that total sum, if anything? Now, we don't have that much information to actually go on here. The only information that we have to go on is the fact that the integral from 1 to infinity of f of x dx is equal to 8. And first of all, as a total aside, 8 was probably not a great number for me to choose. I think it's really clear that 8 is a bad estimate at this point. And I think if we weren't in a quiz setting, if we were just chatting about this out loud, somebody would have pointed this out to me. This is probably, I should have probably put something like 18 or 50 or some larger number, right? The reason being that the integral from 1 to infinity of f of x dx is really supposed to be, oh, let me change my color. Right, so the integral from 1 to infinity of f of x dx is really supposed to be all the area here, right, sort of trailing off towards infinity. So it's supposed to be all of this area here. And that area is definitely larger than 8, right? We can even just count up a few different squares, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this is already like well above 8. So that is an example of why maybe this was not the best prompt or not the best problem. I should have included a larger number here just to make it more realistic. So for that, I apologize. Nobody called me out on it, but it's possible some of you might have been thinking that. So That being said, though, let's assume that the total area is equal to 8. That total infinite integral is equal to 8. And let's try to figure out what this series might be equal to. And we have these 6 bullet points to choose from, right? So our answer should be one of these 6. And so maybe the first thing that I can conclude, sort of straight off the bat, if I'm trying to conclude something about this infinite series, I can conclude, it's not much, but it's something. I can conclude that the sum as n goes from 1 to infinity of a sub n is finite. Right? That is something I can definitively conclude, which means that it is not the case that it diverges. Now, how do I know that? Well, I know that because I can use our integral test to help us out, right? The integral test said that if I have a sequence, oh, whoops, I realized as I slid down, my markings don't stick with the, interesting. Let's fix that quickly. Okay, we're back. Sorry about that. So, how do we know that this infinite series is actually finite? Well, we can use the integral test, right? The integral test said that if I can equate a given function, f of x with a series or a sequence a sub n, then I can compare the series, the sum, as n goes from 1 to infinity of the a sub n's, I can compare that to the integral from 1 to infinity of f of x dx. And I can do this when my series, or I should say the terms of my series, are all positive and they're all decreasing, which is what we see is happening here, right? If I were to fill in several more of these points, we see that all of these points are above the x-axis, they're all positive, and they're all decreasing. So as long as I'm in that world where we have a series in which the terms are decreasing and in which the terms are positive, then we know the integral and the series either both converge or both diverge. And since this integral converged to a finite number, it converged to 8, it is definitely the case that the series converges as well. So this definitely converges to some finite number and it does not diverge. Now, how can we figure out what it converges to then, right? Because which of these remaining 4 to 5 bullet points should this be? Well, there's a few different ways that we can proceed. What we discussed, I believe in the YouTube videos and then again in Wednesday's class last week, is we talked about measuring the values of the series by constructing what kind of looks like a Riemann sum, right? Just an area of a bunch of rectangles, each of which is of width 1. Right? So let's think through this. This first rectangle, it has a height of a sub 1, it has a width of 1, and so the total area, right, the area is a sub 1 of that rectangle. Similarly, our second rectangle here, its height is at a sub 2, right? That's at height a sub 2, its width is 1, and so its area is a sub 2. And so on, right? The area of the next rectangle is a sub 3. The area of the rectangle after that is a sub 4. And so this infinite sum, right? This infinite sum that we have over here can really be thought of as adding up the areas of all of these different rectangles. And here I'll go ahead and draw a few more of them here, right? So all of these rectangles constitute or represent sort of visually a single term. And by adding up the areas of all these rectangles, we're adding up all of the terms in this infinite series. So what can we notice about the relationship between these rectangles and the integral itself? Well, the rectangles are really overestimates of the integral, right? They have this extra piece that's sitting above the function. And that's true with every single one of these rectangles. So what does that mean? Well, we have our function that is decreasing. We have this integral, and I'll write this in red, right? So if I have the integral from 1 to infinity of f of x dx, right? And that's going to be all of this red area down here, which we had drawn previously, right? So if it's going to be all that red area, then if I want to compare that to this infinite series, right? Well, the sum of the infinite series is just the sum of the areas of all of these rectangles, and all of the rectangles sit slightly above the integral. And so we actually get this inequality, right? That the sum of this infinite series will actually be bigger than the integral in question, right? The area of all the blue rectangles has to be bigger than the area of the red shaded region. And so what does that mean? Well, if the area of the integral, right, if that area is equal to 8, that means that our total series also has to be bigger than or equal to 8. So we've actually are able to eliminate these first 2 bullet points as well. Okay, so we've really got it down to 2 bullet points here. I mean, it's possible that we can't conclude which of these 2, but we can definitely conclude something. So it's going to be one of these 2. I'm going to make an argument that says it actually is supposed to be this one right here, right? So it'll be between 8 and 12. And let's take a look at that. I'm going to clean up my workspace a little bit. So let me go ahead and erase some of this. Go ahead for the moment and erase that. Okay, so here's my workspace. What I previously had was an overestimate. But I want to play this game that we discussed in class where I erase the first term, right? I erase the first term, and then I'm going to slide all of these rectangles 1 unit to the left. All right, and so let's keep track of what we're doing. We're starting at the moment. The picture I have right now, which I want to draw in blue, the picture I have right now is the sum as n goes from 1 to infinity of a sub n. If I go ahead and I erase that first term, right? First, let's take a note of what a sub 1 is. A sub 1 in this picture is just equal to 4, right? So not only was this area equal to a sub 1, area equals a sub 1, but this area was also equal to 4. So if I go ahead and I erase that first element, right? Erasing that, and boop, I get rid of that. Well, that's the equivalent of taking my full series and subtracting that first element, which was area 4, right? So I could write that as, maybe I should write that as minus a sub 1. But I can keep in mind that a sub 1 is really equal to 4 here, right? So I'm subtracting that first term. And what we're left with is this sum, right? This is the sum as n goes from 2 to infinity of a sub n. So it's the same thing as before. We're just starting with a sub 2. And then I'm going to play this game where I take every single one of these and I shift them 1 unit over to the left here. So let's go ahead and give that a try. So I erase, right? I'm going to shift. And now I want, maybe I'll highlight what happens here in this first rectangle. So the first rectangle previously looked like this. But when I shift it 1 unit to the left, it's going to look like this, right? Using our Riemann sum language, it's going to go from being a left endpoint Riemann sum to being a right endpoint Riemann sum. And the same thing will happen here, and here, and here, and so on. Let me go ahead and draw out the next few of these. So what we're seeing here, right, is I haven't actually changed the total area. This is still the sum as n goes from 2 to infinity of a sub n. The only difference is where I'm drawing it in my picture, right? But when I draw it in my picture this way, we can make the really nice observation that if I wanted to turn around and compare this to the integral from 1 to infinity of f of x, right? Well, again, that would be all of the area under the curve to the left of x equals 1. In this case, that would become a larger value than the sum we're currently looking at, right? Because the total integral has all of this extra area. It's going to be the area of all those rectangles plus this extra area here and here and here and here, right? And so what we actually see is we can draw this conclusion, right? That the sum as n goes from 2 to infinity of a sub n is less than or equal to f of x, or the integral of f of x. And the integral of f of x, as we remember, that was just equal to 8. And so what have we done here? Well, we actually have this nice conclusion, which I'll rewrite here in the center. Here, I'll go ahead and rewrite it in this orange box here. What we've just concluded is that the sum from n equals 1 to infinity of a sub n minus that first term, which we said was equal to 4, well, that is going to be less than or equal to the total integral, which we said was equal to 8. And so therefore, the sum as n goes from 1 to infinity of a sub n is less than or equal to 12, right? We can just add 4 to both sides of that equation. Okay, great. So to recap, we could actually draw a surprising number of conclusions based on manipulating this picture. Some of them more advanced than others. At bare minimum, I wanted us to be able to know that this series definitely converged, right? The series should converge because the integral converges, and our integral test says that when the correct circumstances are present, those should both be true. They should either both converge or both diverge. In this case, both converge. Second, we should definitely have been able to figure out our first inequality, that the sum of a sub n is greater than 8, by doing our initial rectangular argument. The final piece of the puzzle, the slightly more advanced maneuver that we did right here, required a little bit of a stretch, but was still grounded in the material that we talked about in class on Wednesday. So slightly more advanced maneuver, but I think one that is well worth sort of thinking about or internalizing. It's actually kind of awesome, right? That we can just sort of do this sort of infinite, every rectangle take one step to the left, and all of a sudden we have this new expression that we can examine. So anyway, that's just a quick recap of what I think was a very challenging yet very interesting quiz question. I hope you all are having a great weekend, and I will see you all next time.